Hello, everyone. This is Ted Wertheimer, and it's a pleasure for me to talk today about the Marc 2014 release. Before getting started, I can say that as of today, July 30th, the version will be available on the download site for you to download and use in your engineering work. So very briefly, what we're going to be talking about today is we're going to be talking about new enhancements in geometry and CAD technology, in meshing, in, of course, contact, in terms of improving the performance of the solver, pressure cavity calculations, fracture mechanics, circuit analysis, a little bit on composite orientation, and then platform support and licensing. So driving into this is really over the last few releases, we've had an evolution of the technology associated with CAD and meshing in the MenCat product. And that technology really went from what we used to use, which was the ACES geometric engine, to what was introduced in MenCat 2013.1 is the Parasolid geometric engine, and now in 2014 with a new set of CAD importing tools that import directly into Parasolid. So one of the reasons we went to Parasolid is because it allows us better compatibility with the other MSC products, such as Patran and SimExpert. It also allows MSC as an organization to do basically the meshing development and be able to share that between these different products. So what the good news is on the import of CAD, you will now see two levels of methods of doing CAD import. One is importing directly as a solid, which goes into the Parasolid framework, or still the existing one where we do CAD import and then it goes into a representation that looks like a set of tessellated surfaces. Along with that is a new set of solid entities, which is really completes the family that exists in Parasolid. So we have solid type entities, and then we have a new set of entities which involve what are called sheet bodies, which are planar in nature, or effectively wire bodies, which you can think of as beams in nature. So the beauty of these new sheet type entities is that we can do operations similar to what we used to be able to do on discrete finite elements or nodes, but what we can do to them is we can expand them, so we can take a sheet body and we can revolve it, or we can drag it, and then of course what the end result is a three-dimensional entity associated with it. The other thing is because it's all in a unified solid representations, we can do Boolean type operations. So again, if we would think about these two sheets and a cylinder, we could basically unite those two sheets to get a single sheet, which will help us in terms of meshing. And then of course we can subtract the cylinder from the sheet and effectively drill the hole through this. So it's an easier way to do it, but the real gain in this is really that we're much more compatible with the rest of the CAD/CAM industry. So what this allows us to do is not only represent these solids, but to import these solids from other CAD systems, and we've expanded our inventory of CAD system support in terms of supporting now TIA V5, SolidWorks, and Inventor on Linux, a completely new CAD CAD interface, which is called JT. We have improved CAD cleanup operations too that I'll get to a little bit later, and we have improved defeaturing operations all within the MenCAD product. So really what that means is you don't really need to have multiple solutions when you're doing nonlinear simulations with Marc. You can effectively, from Marc and MenCAD, you can really do everything you need in terms of getting from somebody else's CAD representation into a finite element mesh. So as I said, the new button to look for under File Import is Import CAD as Solid. And then, of course, we have our type, and we can select any one of these particular CAD systems. You might notice that VDAFS is not in this list. It is still in the other method of importing CAD to tessellated surface, but we anticipate retiring VDAFS and actually DXS in a subsequent release. When one has this, one can basically import the geometry, one can do some filtering, so one can get rid of wires, and they're often used in piping systems that might not be necessary. And then you'll see a series of tools that you can use to clean up the different CAD geometry. And we're going to take a look at that a little bit in detail. The first one really has to do with changing the mathematical representations of surfaces. That's pretty much for the advanced user. This one is a little bit more useful, but there are two places that you can do this. This is basically considering defeaturing the geometry on import. That's one way of doing it. We will also see that there's another way of defeaturing the geometry after you've already brought it in, and that gives you a little bit more control. And then there's a set of some advanced features, which is really, again, it's really trying to get rid of little holes in the geometry. The most important one is this one here, what we see here, which are known as healing and sewing. And we'll see an example where doing healing and sewing was necessary to clean up some really bad geometry. The good news is for most of the models that we've seen, and the tool that we're using, as I say, is used now in some of the other products from MSC. There have been well over 1,000 test problems used and verified to make sure that these tools are useful for CAD import. So this was an example. It's actually an IGES file, and one can say IGES files are the absolute worst in terms of representation of the body. But if one would have turned off healing and sewing, one would have saw a geometry, and there actually would have been these giant holes in the geometry. And then by activating healing and sewing, what happens is that the geometric representations of the surfaces, the mathematical accuracy becomes a little bit better, and it recognizes this as one continuous body, which means that now if we generate a finite element mesh on it, we'll truly have a finite element body that represents the whole structure. So how does this look like in when we run MenCAD? If we would have gone in and imported this geometry, and this is what it looks like in this form. This was also an IGES model, and we included heal and sew on, and that was actually important for this structure because without it, it actually looked like a bunch of flat bodies. one will see that directly in the model tree or the model browser, it will demonstrate that there were actually 6 solid representations of this body. And you can basically say identify solids, and it will color code the solids, similar to what we do when we color code other types of operations. Other commands that can be used are the select control. This is very useful, that you can basically say select a particular solid. You can say select it by a particular thing. You can select it by type. And if you would have imported everything, you might have seen all of a sudden some loose wires or 1D items. And so one could easily select those wires and eliminate them. Or you might get extremely small surfaces or extremely small solids that are, something that the CAD system gave, and you can basically select those minimum geometries and then, of course, eliminate them as well. Or, of course, you could have filtered them out right from the start. So we'll see this a little bit later, but of course, we're engineers. We're interested in obtaining the stresses in the structure, the thermal behavior of the structure. So the real power of what we can do when we can import the geometry directly into Parasolid is that we can simply press one button and it will mesh all the solids. It will figure out what is appropriate element size. So these regions that have higher curvature or are smaller bodies have finer meshes in them. And then you can press another button and it will put each one of those collection of elements that were in the Parasolid representations into their own contact body. So an operation that used to take hours in the old method of importing a CAD, putting on seed points, matching the seed points, generating surface representations, and then from those surface representations to a tetrahedral solid representation, that's an orders of magnitude easier and faster with the new MenCat product. As I mentioned before, there was an early way of doing defeaturing, and then there is, after you bring in the body, you can also do defeaturing. And this allows you to very selectively go in and say, I have holes and I want, holes less than 2 millimeters to be eliminated. You would set the size of your hole to 2 millimeters. It would find all those holes. Or you could then remove them, or you could look for an individual hole, select that hole, and move it. If it would be a part-way filled hole, not an all the way through, you could raise it and lower the height of it. And there are a whole lot of different operations that you can use to, eliminate some of the issues that are associated with the design. Of course, I'm going to say we don't always want to remove the holes, right? Because often the holes are where the stress concentrations are. So, of course, you have to balance your engineering judgment as to what you should save and what you should remove. So this was our little part to start. And you can see we selected a variety of features. And there was this giant fillet over here. And we said, remove the fillet. And the fillet was disappeared. And then we said, we selected this particular hole, and we said, increase the hole radius, and the hole radius increased. Or here we said, take this particular hole, that was over here, and then we said move that hole, and that particular hole moved. So those are the types of operations that can be done. In terms of a real-world problem, here you see what on the model browser, when we do defeaturing and we select holes or other types of features, all those features are identified on the model browser. And in this particular problem, based upon the hole size, and there were 7 of them, you might say that some of these are pretty big holes. But just for the fun of it, we decided to eliminate one of the holes. So we selected that particular hole. And you could have done that by either clicking on the hole or using the right mouse button on the particular item in the model tree, and that would have identified the hole. And then we deleted the hole, and then we basically generated the finite element mesh, and you can see that that hole effectively, which went all the way through the cavity, is eliminated. So that's a demonstration of the new CAD type technology. In terms of meshing, we can now mesh directly on the parasolid representation of the geometry. So if we had this particular sheet and we said I want a quadrilateral dominated mesh, we can press one button and we get the mesh. If we say we want a triangular based mesh, again, we just say triangular based mesh and we get the mesh. 2 things are important. One is, of course, considering the curvature control in the geometry. And the second thing to recognize is this can be done with either lower order elements or higher order elements. And when you use the higher order elements, it will put the mid-side nodes on the geometry. The second thing to recognize is effectively you could generate a lower order element mesh and then say do a change class, go from a lower order to a higher order. But in fact, doing it directly as a higher order element is the more accurate thing to do, especially when you have regions of concave type surfaces. So the trick on this is we can either specify seed points just like we used to, or we can basically say give me a mesh that's of a uniform size throughout the particular region. So here we have only one geometric body. You can see again we can use the defeaturing tool to recognize where this fillet was. Here we see that there were 2 holes in the model browser and 1 fillet. And you can look at the amount of control that you had on the tool. So here we basically said we were targeting an element size on particular edges of the solid representation, and then we had additionally a target element size for the whole world, which was a bigger number. So where does this really get to be powerful is really larger assembly models. So if you took a look at this structure and you said, I want to mesh this with MenCat today, with the version 2013 or 2013.1, you'd recognize that you're in trouble. At first, you would import the body in, and you would see that you got a lot of junk. You got a bunch of minimum bodies. You got some wire bodies that you weren't interested, and you got some solid bodies. And you'd want to get rid of some of those. And using the select tool that I mentioned before, is a good way to get rid of minimum bodies and wire bodies, and that gives you an easier representation to model. In this particular structure, if you didn't use heal and sew, you got about 70 solid models, 70 solid bodies. But if you did heal and sew, it would do the necessary geometric cleanup to get a better representation of the geometry of the structure, and in fact the structure had 93 bodies. And when you said, I want to mesh it, what the program will do is, if you do by default, which is basically saying automatic and figure out the best mesh size for each one of the bodies, including the fact that I want to incorporate curvature check. You will look at each body, figure out the best element size, and mesh the structure. So in this first one, that's what we did. And you can see the finite element mesh. And it ends up that within this one area, there are basically ball bearings in the structure. And this is where, using the incorrect technique, you didn't get all these ball bearings. So the good news is basically I was able to import the structure from a CAD system and mesh it in 3 minutes. And so this is a huge savings over the procedure that we would have needed to do previously using MenCat and many other systems as well. Well, you might have said that, 3.3 million elements is a little bit too much, even though depending on what you're doing with it, that's not really such a large model in today's system. But you could have said, okay, I want bigger elements. I don't need that level of resolution on the whole structure. Or you could say, I want a coarser resolution on each particular body. So I just said do it on the whole structure, in which case importing the structure and meshing it took 70 seconds. And I got substantially less finite elements in the model. So these are very powerful tools, but of course the key thing is the simulation. So we always do some enhancements with contact. As we said in the last few releases, the approach using segment to segment we think is the better approach for simulation. We're slowly but surely moving and doing more options with segment to segment. But we also recognize that there were some numerical issues with the previous version. So we've modified or potentially modified the defaults that are used to determine penalty factors and augmentation and things like that. But of course, we have to maintain backwards compatibility. So we have a new switch for version number 2 when you're in the job menus, and then you go to segment, and then you'll see this version. So version 2 is the newer version, and it really controls 4 things. One of the things that it controls is the penalty selection and how it chooses the penalty when you have 2 bodies that have similar stiffnesses, or how it chooses the penalty when you have 2 bodies coming into contact with one another, where one is very stiff, let's say steel, and the other one is much softer, let's say some sort of plastic. So the choice is a little bit better tuned so that you reduce the amount of penetration that might occur, and you get faster convergence in the numerical scheme. The second one is what we've called augmentation. augmentation was activated if it said penetration is occurring, and it was activating the augmentation, let's say, at too small of a distance of augmentation. And augmentation is a little bit expensive, so that distance associated with penetration before augmentation is triggered has been increased. So what that means is you'll still get the accuracy. You'll still attempt to get zero penetration, but the augmentation will be activated later, and that will reduce computational costs as well. The third one has to do with friction. With friction, we also have penalty factors in augmentation procedures, and that penalty was constant throughout the whole model. And of course, we're doing nonlinear analysis, so anything that's constant is probably not the optimal solution. So we've modified that in 2014 release. So we look at the normal stress and contact, and then we change the penalty, the augmentation penalty, to be more effective. What that means physically is that at lower stresses, you'll see effectively more slip occurring, and at higher stresses, we'll have a higher augmentation penalty, and you'll see less slip occurring. And then finally, what we've done is, in terms of separation, separation between node to segment and segment to segment is different. With segment to segment, it's really effectively more accurate. We check for separation at every Newton reps and iteration. That would cause higher costs and possibly a failure to converge. So we have changed the way we count cycles, reducing the chances of a Marc exit 3002. So here are a couple of very simple examples, looking at the original body and then the deformed body where we have self-contact, and then the final stresses. And the thing that we're interested in is really the number of iterations, because the bigger the problem, the more the number of iterations influences your computational cost. And you can see that the segment-to-segment procedure that was previously available, still available today, was less than the node-to-segment procedure, and using the new modified defaults, it's substantially less. So when you have problems that are driven by the solver time, you may see as much as a 3 times factor improvement in computational costs. Similar in looking at a 3D type of problem. Well, when we use this problem that goes into self-contact with node-to-segment approach, we actually saw, and this was also using local adaptive meshing, we actually saw penetration. When we use the segment-to-segment approach, because of this issue with separation and cycling, it failed to converge, and with the new defaults with 2014, we successfully complete the analysis. As I mentioned, we're always trying to expand the number of options that are being used with segment to segment. We recognize that certain capabilities, let's say like mechanical wear, are not yet available, but in 2014 we added the breaking glue option is now available as well, both for 2D type problems and for 3D type problems. Computational performance, there really were actually 3 things that were done, of which only 2 are mentioned. One is, as I just mentioned, in terms of speeding up the contact. The second is, as many know, in 2013.1, we introduced parallelism in the element loops for shared memory parallel. Everybody uses multi-core chips. It is a very effective way to reduce the computational time. I personally always use this particular option today. It wasn't available in 2013.1 when combined with ELSTO. It is now available in conjunction with ELSTO. The other improvement that has been done on performance is the Paradiso solver had some issues with out-of-core solution techniques. Some of those problems have been eliminated, but we also know that the Paradiso solver still is using more memory than our conventional default solver. But again, I strongly encourage people to use the Paradiso solver because it's much faster. Pressure cavities. We have had for a long time an option where we could take a cavity, fill it up with gas. Either the amount of gas could be constant, or you could increase the amount of gas, and then as the cavity would close, then the pressure effectively increased. Well, this has now been complemented with the capability to not only use a gas that satisfies the perfect gas law, but with a liquid that is nearly incompressible. So you would need to enter in the bulk modulus, or effectively the compressibility associated with your liquid. And then there is a stabilization factor as well. So the other thing that was done on this is the pressure cavity capability used to only be available where we recalculated the volume once per increment. We now recalculate the volume on an iteration by iteration basis. So we can take a look at this particular field that we're going to close, and there are 3 cavities. The first 2 have a gas, the third one has a liquid. You can see that this cavity, the volume is effectively the same. You can plot the volume versus time. Sorry that this is in yellow. And that would be the liquid-filled cavity, and these would be the gas-filled cavity. So it's a very useful option. In the area of fracture mechanics, this is again an area that really each release for the last 2 or 3 years has shown some new technology. We've improved the geometric behavior of the crack front. That just looks better, and we basically get smoother results. But the key thing, or one of the key things, is allowing the calculation of fatigue of the amount of cycles such that the crack moves a certain distance or grows a certain distance. So everybody knows we have SN diagrams and EN diagrams that are available in actually in MSE fatigue, which is a product associated with Patran. This is a different method of calculating fatigue. So we've improved the cracks and sharp edges. We've improved self-contact. We'll get to that. And we've done something for the termination option. So what we really do in these types of calculations, we usually have some sort of structure. We can either postulate the location of a crack, or we can use the other options to initiate or say, based upon stresses, where that initial crack is supposed to be, using what's known as a template mesh. And we're going to use Paris's law to determine how the crack is going to grow, or we can use some other mechanism in conjunction with Paris's law. If we have multiple cracks in the structure, and what we can do is we can say this is your basic law to define the crack growth amount, and then you can say I want to scale the crack growth amount based upon the local behavior at a particular crack, let's say based upon the stress intensity factor or the energy release rate. So we see that over here, this crack on the larger hole is actually propagated a greater amount of distance. We'll get back to that example again. The other one is what I said in terms of smoothing out the crack surface. So here we had a structure, and you can see that it has different heights here and here because we wanted to have something with a non-uniform stress distribution. We postulated where a crack is going. We're going to move these red surfaces up and down. And what effectively would occur before, so let me go back to the previous one, what we're really interested is how the crack grows in this direction and also how the crack grows in that direction. In other words, how does the crack face change? And what one can see is if one did the default, we got a crack face that looks like this. This is much smoother than it was in the past. In the past, you would have had all sorts of oscillations here, so we locally smooth things. And then we can scale things to determine what sort of procedure for the crack evolution. So going back to fatigue, what we're really going to do is we have to perform a few cycles of analysis even to study high cycle fatigue. So again, it's more expensive than conventional SN diagrams, EN diagrams, or using Miner's rule associated with linear fracture mechanics. Then we use, again, Paris's law to determine the number of cycles to achieve a certain crack length. And of course, we have new user subroutines as well. So what one would have obtained here, and if you do the appropriate scaling, you'll get a number that basically says if my crack was initially 0.1 in length, for my crack to grow to 0.13245, it would have taken 10,660 cycles. That's the information that you obtain. So we obtain the incremental fracture mechanics quantities. We look at the incremental crack growth, and we determine the cycle count based upon that. So you can see how one of these cracks might grow in 3D as well. And this is what you would have seen for that particular crack. The crack had a certain length. To grow it a little bit means basically you don't need any cycles at all. To basically grow it to this length, it would have basically said you needed around 8,000 cycles on this particular structure. Pretty weak. Again, more accurate evolution of the crack geometry, better ability to deal with cracks that change directions, smoother crack outlines. The last thing on fracture mechanics is that we have an ability that if you don't know when something is, what stress level something's going to crack, you can apply an arbitrary load, and you can use the termination option to say, once the crack initiates, stop applying that load, and now apply my cyclic load to determine the crack growth and to obtain the cycle count. What was necessary to do this, when you think about cycling, you think about the crack opening and the crack closing. So we've improved 3D self-contact with remeshing as well. So here's a problem that we would have always gotten an unfortunate Marc exit message before. So we can see that we can get these surfaces to close for a longer distance. We can remesh, and we don't get or less likely to get the previous error message. Finally, moving on to electromagnetics, we've introduced what's known as a circuit approach. Previously in Marc, when you had an electromagnetic problem, you had to apply a current. And that's really not what's going on in the real world. We know that because we look at an electrical outlet on the wall, and it says 120 volts, at least it does in the US, 220 in most of the rest of the world. And then, of course, we have circuit breakers that say 15 amps, but that just means the maximum number of amps. So now you can apply that voltage across the system. And of course, we're really driving for problems that are both electromagnetic and thermal, or electromagnetic and structural. Looking at the electromagnetic is when we get our really known answers. So we can look at the magnetic induction around a coil. If we would do a magnetodynamic problem in the frequency domain, we would be able to determine how that inductance varies with the frequency. But we're interested in structural problems, so kind of looking at a solenoid, and this is effectively the plunger, and this particular region was air. And what we can do is we can look at the magnetic field or the magnetic induction in this whole range, and then we can basically do, in a single analysis, we can do the coupled thermal structural electromagnetic problem. So this was actually a dynamic problem, so you actually see the plunger wiggle a little bit. Another area of application of interest of this is induction heating, and of course induction heating in conjunction with manufacturing type problems, such as the rolling of this sheet and forming it into a so-called continuously welded pipe. And so what we really have here is we have a fine mesh representing the air. We have our coil that is where the electromagnetic behavior comes from. We have some structural rollers, and then we have our sheet. And so we can look at things like, what is the temperature associated with this particular process. But what we would really be interested in is we'd really be interested in how well it welds together. So we can see that what we can get out of this. We can look at the temperature profiles during the simulation as the tube is being rolled forwards by those rollers and coming together. And so we effectively are gluing the rolls together once contact is achieved. Or we could look at the plastic strains during this formation process as well. You can also, of course, you could cut through a slice. You can look at the magnetic potential in the air. This would effectively represent the leakage that occurs, and one can cut in different directions on the structure. Finally, I want to talk a little bit about platforms. The Marc 2014 release is available on Win 7 32-bit and Win 7 64-bit. We have moved to a new compiler from Intel, which slightly improves the performance. The good news, if you would buy a new computer, that's what compiler would be on your machine. But the good news is the compilers that were used for Marc 2013 and Marc 2013.1, they also work with this newer system. So we made sure that that was working as well. We show here Linux Red Hat 5.7. That's one of the operating systems. We also support Red Hat Linux 6.3 and SUSE 11 Service Pack number 2. So on the download site, you'll see that you have more choices in terms of what you're going to download. The key one is the Marc 2014 release. As we documented in 2013, this will be the last release on 32-bit Windows systems. The other thing that's hardware related is we've introduced a 3D spaceball device, and that spaceball device might have additional buttons, and you can program those buttons to do what you want them to do. So the three things that were there before, translation, rotation, and zoom, was achievable, and now you can do other things as well from the click of your hands. You're more coordinated than I am. Finally, the CAD capabilities, Cad Import capabilities, are a new capability in MSE in the Marc 2014 release. So everything that was there before still exists. The older general CAD and surface elements still exist. Those are in yellow. One needed to have an additional license to get those. If you had a license for any of these products, then you would automatically get a license for the new capability, which is general CAD as solid. If you didn't have one of these licenses, then one is going to need to go to your friendly local MSC salesman and acquire an additional license. The good news is not only are these much more powerful than these are, they are also at a lower price point than these are. So we are going here soon to the end of the year. I'm sure this is a great opportunity for you to use a little bit of your extra budget to improve your productivity and get these additional CAD features. So I want to thank you very much for your attendance at today's seminar. I want to again thank those people who were beta testers of the Marc 2014 product. They help us make sure that it's a more reliable and a higher quality release. So I think we have some time for some questions. Thank you again.